Kartis.
Awesome. Thanks so much, John. I'll go ahead and share my screen. All right, so I want to tell you all a story today about what it'll take to decarbonize the world around us. And so I like to always start by putting up this image and just asking us to think about where the carbon footprint is. And you might instinctively point to the gasoline-powered vehicles, to the electricity powering the lights. Those are carbon footprints that we're really familiar with. But there are also carbon footprints behind virtually everything that you see in this image. There's a carbon footprint behind the plastic of the billboards, behind the clothes that everyone's wearing, behind the steel of the flagpoles, the cement of the buildings, even behind the patty of the McDonald's burger. So these carbon footprints are truly inescapable. So we can think about this problem quantitatively. This plot shows the carbon footprint behind the top 18 commodity chemicals, which then go into manufacturing the material world that we constantly interact with. And you'll see here that one chemical, ammonia, has such a large greenhouse gas footprint that it actually has its own y-axis on the right-hand side. So if we're serious about decarbonizing the material world, we have to do something about decarbonizing ammonia production. Now, beyond that, if we are serious about deep decarbonization, that is extensively decarbonizing the material world, then we do also have to do something about ethylene and methanol and propylene, ethylene oxide, BTX. There are a whole bunch of chemicals which each have a smaller slice of that carbon footprint. So we have a really big challenge ahead of us to decarbonize the material world. So you might just think at the outset, well, if these chemicals have such a large carbon footprint behind them, why not just stop making them? And the truth here is that something like ammonia is essential to our quality of life. That ammonia is then used as a fertilizer to grow foods that we eat. It's used as a disinfectant. It's used to produce fabrics and plastics. So even though there are always opportunities for increasing efficiency or how we utilize a material, this is a material that we only expect to grow in importance going forward as the world population grows and as quality of living standards rise as well. So let's briefly consider how we make ammonia today and why it contributes so much to the global greenhouse gas footprint. This is actually a picture of a Haber-Bosch plant. This is how we make the world's ammonia today. This is a chemical plant that costs about $2 to $3 billion. So this is an enormous investment that's made to manufacture an important chemical that we use in our everyday lives. This process starts with methane and water. These are reacted together in a process known as steam methane reforming at greater than 700 degrees C, along with a secondary reaction known as water gas shift to produce hydrogen. And this reaction in the process creates a stoichiometric CO2 footprint. So this is a side product that one has to contend with here. That hydrogen that's produced is taken into a second step where it's reacted with dinitrogen taken from the atmosphere to make ammonia. And this is done at 400 to 500 degrees centigrade and 150 to 250 bar. So our two major problems then first are this enormous CO2 footprint, which just comes from the rearrangements of these carbons, hydrogens, and oxygens. It's unavoidable in this first step. And the second major problem is that we have really high temperatures and pressures. These are conditions that make it such that this chemistry has to be practiced in a centralized fashion. This is something that you can't just do in your garage. And I'll talk later in this, during this presentation about why that centralization is a detriment to the world today. So we can consider an alternate paradigm. This is what our group is working on at MIT to electrify chemical manufacturing. And in this paradigm, we start with CO2 and nitrogen. That nitrogen could come from the atmosphere. CO2 could come either from the air if we have direct air capture technologies, or from point sources. So for instance, from the effluent of a fossil fuel power plant. We then react that with water and putting those together with renewable power operating at 25 degrees centigrade and just 1 bar of pressure.
So basically,
we aim to make diverse chemicals that we require. So these are things like fertilizers, paints, carbon fibers, and plastics. There are a whole bunch of things that we aim to make, beginning with just these very basic feedstocks. So in this paradigm, the reason that CO2, nitrogen, and water are desirable is that these are ubiquitous feedstocks. They're available everywhere. And with just these 3 molecules, we have access to 4 elements: carbon, oxygen, nitrogen, and hydrogen. And we can learn to stitch those together and make more complex things. Renewable power is important because it enables sustainability here. If we can power these processes with solar and wind, we can overcome the current use of just burning hydrocarbons as a means of generating heat to drive chemical reactions. And that would be a significant step forward in sustainable chemical manufacturing. So let's take a look at what this might look like if actually implemented. We could try to react nitrogen and water to make ammonia, and the process also generating oxygen. We would do this at 25 degrees centigrade in 1 bar with renewable power. And so this image shows how we could perhaps implement this. We could have a solar farm generating solar power, feed that to a small neighboring device, which takes that solar power, as well as water from a neighboring source, reacting nitrogen in the air with this water, using renewable power to make ammonia, which can then be used to fertilize a neighboring field. So this would overcome the existing centralized manufacturing paradigm that we have. This process also doesn't generate any CO2, and you can see that from the overall balance here. By replacing methane with water alone as our hydrogen atom source, there is no CO2 footprint. So this would be a clean and sustainable process that operates at ambient conditions that can make ammonia close to where it's actually needed. We've actually built a prototype of this in our lab. So this is the prototype that today holds the world record for being able to make nitrogen and water into ammonia at ambient conditions. In this prototype, one first takes water, breaks that down to make hydrogen, then takes that hydrogen and feeds it to a second step where that hydrogen is reacted with nitrogen at ambient conditions to make ammonia. So we've actually enabled this overall reaction. This has been probably one of the most challenging projects that we've undertaken in our lab. That nitrogen triple bond is really difficult to break, but it's something that we've been able to get a handle on and learn how to break that bond even at ambient conditions. So you might be wondering why we didn't do this already. If this paradigm of using electricity to do chemical manufacturing is so appealing, why didn't it occur decades or a century ago? And a lot of this has to do with the fact that we have a new opportunity when it comes to the fact that renewable electricity is getting so much cheaper. So if one looks at dollars per watt for a solar panel, it was $76 per watt in 1977, down to just 25 cents per watt in 2017 and continuing to drop today. This means that renewable electrons are as cheap as they've ever been and will continue to get cheaper. There are aggressive estimates that place us at 1 cent per kilowatt hour in another 20 years. And if electricity is just 1 cent per kilowatt hour in 20 years, that is going to completely change how we think about driving energy intensive processes like chemical manufacturing. So we've talked about the need for making ammonia in a sustainable fashion that would help us achieve our decarbonization targets. But there's another really important problem here, which is access to fertilizers around the world. This plot shows the price of urea. Urea is an ammonia-based fertilizer for many countries around the world. So, in sub-Saharan Africa, so this is Burkina Faso, Cote d'Ivoire, Ghana, Mali, Nigeria, and Senegal. Their fertilizer prices as compared to the international average. And you'll see that these countries are paying 2 to 3 times the international average. And this has been a stubborn problem. This has existed for decades and decades. And despite the efforts of many organizations and governments, this problem has not been overcome. The reason for this is that there is poor infrastructure for distribution. Fertilizers all cost about the same up till they're brought to port. And then this process of getting them from port to where they're needed is much more expensive in sub-Saharan Africa. So the issue here is that investments in that infrastructure are very expensive. So this method that we're proposing, one in which a solar panel hooked up to a device can take air and water and make it into ammonia, means that ammonia can be made close to where it's needed, and one no longer needs expensive infrastructure for distribution. So if we're successful in developing these technologies, it can help to solve a very stubborn problem in fertilizer distribution, which leads to many downstream societal harms. This lack of use of fertilizers leads to poorer crop yields, which then has downstream effects when it comes to hunger and other issues. So we could have a lot more impact in terms of agricultural productivity as well. So I've focused in on ammonia, and I want to drive home that this isn't just about ammonia. This is about the other chemicals shown here as well. My lab has developed new methods of making, for instance, ethylene oxide. So routes through which one can take carbon dioxide and water and react those to make ethylene oxide, which is needed for ethylene glycol and diverse polymers. And one needs to develop a route for every single molecule shown here if we're going to have a significant impact on decarbonizing chemical manufacturing. And so that then is the vision, right? Is to make not just fertilizers, but to head towards really decarbonizing the material world so that that carbon footprint is no longer inherited by every object that we interact with. And with that, I'd like to thank the team that we have working on these problems. I think in so many ways, I think I grew up thinking that science was something that an individual could by themselves have an enormous impact on. But I think it is just so true that these are teams that are all building on each other's advances and talking together and thinking together to develop new solutions. So I'm really proud of the collaborative team that we've built that's really pouring their heart, mind, and soul into making this future of a decarbonized material world. And with that, I'd be happy to take any questions.
Great. Like I said, I think this is so timely, you know, as people are thinking about how they can help the planet be more sustainable. Is there a Brookline High student that would like to ask a question live to Kartik?
Yeah, Kate Anderson, one of my faves. I put something in the chat here. Kate, do you want to just unmute and ask away yourself? You're not shy.
Yeah, sorry. Would the use of water cause any issues for the environments that the water is being taken from?
Yeah, excellent point, Kate. We have to really think as expansively as possible and draw the box in which we're doing these analyses or processes as big as we can so that we're not creating any unintended externalities. And this is something that actually a lot of people have missed, right? Is that it absolutely matters where the water comes from. We favor using seawater as much as we can, and we're developing processes in our lab that allow us to use seawater with all the chlorides that it contains and other metal ion constituents in order to drive the synthetic processes that we're developing. Now, there's still some processes that we're doing that require desalinated water, but we're trying to overcome that as much as we can. That's gonna be an important driver of our research in the next decade.
Great. Do we want to do one more question? And as the student is getting queued up, behind me is one of the first personal computers, I thought in honor of our next two speakers. Ed or Jen, do you want to, is there another student you want to ask?
Anya, I saw your question in the chat. Would you want to unmute and share that one out?
Sure. How does the method that you created work? You said it was very hard to break the triple bonds. How much sunlight energy is needed?
Yeah, excellent. I'm glad you're thinking about the energy footprint and how we actually, what tricks we use to help to break that bond that is ever so inert and strong. So we're actually using a lithium-based catalyst. Lithium is really special as a metal for the fact that it can break the nitrogen triple bond spontaneously at ambient conditions. So we're leveraging that intrinsic capability that lithium metal has to drive that reactivity. When it comes to the energy footprint, your question is essential because the energy footprint of this process is actually still rather large. So we're doing cartwheels and somersaults because we're so excited to finally be breaking that bond, but the energy efficiency is not as high as it needs to be. Right now it's around 2%. We have a target of reaching about 25% in another few years. If we hit 25%, we think it'll be commercially viable. And that, at that point, we'll be using that energy content from sunlight in an efficient enough manner to actually make this something that could be commercialized.
Great, thanks, Kartis. Next.